Here's a question that sounds ridiculous, but if you've used any AI in the last 2 years, you've experienced it firsthand. Why can ChatGPT write you a sonnet about quantum mechanics, debate the moral implications of artificial intelligence, explain the political tensions in the South China Sea, and then immediately fail to multiply two 5-digit numbers? It's not a glitch. It's not a bug you can fix with an update. It's the architecture. And understanding why it happens. Why an AI that writes like a philosopher can't do what a $2 pocket calculator handles without thinking. Unlocks something genuinely surprising about how these systems work. Because here's what a team at a company called Percepta showed us. You don't fix the problem by making the AI better at guessing. You fix it by turning the AI into a computer, not a manager that calls out to a calculator. The AI itself becomes the thing doing the arithmetic. In March of 2026, a researcher named Christos Tsamos posted a thread that got 1.77 million views. His opening claim was deliberately provocative. LLMs solve research-grade math problems, but struggle with basic calculations. We bridge this gap by turning them to computers. And he didn't just say it. He showed a transformer, the same architecture that powers ChatGPT and Claude, solving one of the hardest Sudoku puzzles ever constructed. Not approximately, not usually, 100% accuracy every single step. When Andrei Karpathy, former director of AI at Tesla, one of the founding team members at OpenAI, and arguably the most influential technical voice in artificial intelligence, saw it, he wrote, "Wait, this is so awesome. Both the C compiler to LLM weights and the logarithmic complexity hard-max attention. Inspiring." If someone like Karpathy is calling a research project inspiring, it means something real is happening. So how do you put a computer inside a neural network? Before we get there, we need to build up from the very beginning. What is a neural network? What is a transformer? And why, fundamentally, can it multiply? So to summarize the setup, AI can do things that seem magical, write, reason, create, but it collapses at basic arithmetic. That's not incompetence. It's a feature of how these systems are built. A team at Percepta claims they solve this by literally compiling programs into the model's weights. Karpathy called it inspiring. Before we evaluate whether that's true, we need to understand what these systems actually are. Let's start from the ground up. Let's start as simply as possible. Imagine you want to decide whether to carry an umbrella. You look at a few things. Are there clouds out the window? What's the humidity? Did your weather app say rain? What does the barometric pressure look like? Each of these pieces of information sends you a little signal. Clouds out the window. That's a strong signal for rain. High humidity, moderate signal. But the barometer is rising. That's actually a signal against rain. Now, here's the key move. You don't give all of these signals the same importance. Clouds matter a lot. Humidity matters somewhat. The barometer matters a little, but you're not sure how much. A neural network does exactly this, but mathematically. Each piece of information, each neuron, holds a number. And between one layer of neurons and the next, there are numbers called weights. Each weight says, multiply this signal by me. A big weight amplifies the signal. A small weight dampens it. A negative weight flips it. Clouds mean don't rain instead of rain. The network takes all your inputs, multiplies each by its weight, adds them up. And if the sum crosses a certain threshold, the output neuron fires. Probability of rain goes high. That's one neuron. A real neural network has billions of them, stacked in dozens or hundreds of layers. Each layer combines, transforms, and recombines the information from the layer before it. The whole system is a massive chain of weighted sums and threshold checks, flowing from input to output. In a language model, the input is text, a sequence of words and punctuation. The output is a single prediction. Given everything so far, what's the most likely next word? But here's the critical thing you need to understand. The model doesn't know what it's doing. It doesn't understand the weather, or language, or arithmetic. It has learned a pattern of weights that, when you feed it the right inputs, produces outputs that look correct. It's not thinking. It's computing a mathematical function. A very complex one, but still just a function. And how do you set those weights? How do you choose the right multipliers so that the function produces good language? The traditional answer is, you train it. You show the model billions of examples, sentences, paragraphs, entire books, and you adjust the weights over and over, millions of times, each time making the model's next word predictions slightly better. It's trial and error conducted at an astronomical scale. Gradient descent, backpropagation, learning rates, loss functions. The whole machinery of modern machine learning exists to automate this process of adjust the weights slightly. Check if the prediction got better, repeat. This works remarkably well for language. You train on enough text, and the model learns grammar, facts, reasoning patterns, even creativity, all as emergent statistical properties of what word is likely to come next. But it fails spectacularly at something simple. Okay, take a breath. What have we established? A neural network is a function. Inputs get multiplied by weights, summed up, passed through layers, and produce an output. The weights are set by training, trial and error over billions of examples. This works great for language because language has patterns. But here's the problem. Computation doesn't have patterns. It has rules. And that's a fundamentally different kind of thing. The next section explains why language prediction and arithmetic live in different universes, and why the gap between them can't be closed by just training harder. Let's be specific. Ask ChatGPT to add 1,847,392 and 9,284,716, or to be precise, 1,847,392 plus 9,284,716. The model will give you an answer. It will sound confident, and there's a decent chance it will be wrong. Here's why. When the model generates its answer, it's playing a word prediction game. It's going through its vast knowledge of text and asking, what number most likely comes after 1,847,392 plus 9,284,716 equals, in the training data it absorbed? But here's the catch. That exact arithmetic problem is almost certainly not in its training data. So the model is essentially making an educated guess based on the general patterns of addition it absorbed from seeing math equations as text. It knows what an addition equation looks like. It knows the result is probably around 11 million. But it doesn't actually add. It doesn't carry the tens digit from the ones place, then the hundreds, then the thousands. It doesn't execute an algorithm. It guesses. And guessing is fundamentally incompatible with computation. Think about what addition actually is. You line up the numbers. You add the ones column. 2 plus 6 is 8. Write it down. Then the tens. 9 plus 1 is 10. Write down 0. Carry the 1. Hundreds. 3 plus 7 is 10, plus the carried 1 is 11. Write down 1, carry the 1. Thousands. 7 plus 4 is 11, plus 1 is 12. Write down 2, carry the 1, and so on, left to right. Every single step depends on the exact result of the previous step. If you get the carry wrong in the hundreds column, every digit after that is also wrong. One small mistake cascades. That's what computation is, a sequence of exact steps where each step depends precisely on the last. No fuzziness. No, probably right. Either you got it or you didn't. Prediction is the opposite of computation. You don't need to be exact. You need to be plausible. If you predict 11,132,108 versus 11,132,107, both sound plausible. Both could be right in an approximate sense. But in computation, only one is correct and the other one is flat out wrong. So the current solution that companies have adopted is kind of embarrassing when you think about it. We give AI a calculator. When you ask ChatGPT to do math, it doesn't compute it itself. It generates a request to an external Python interpreter. The interpreter does the actual math, and then ChatGPT reads the answer back to you. The language model is essentially a manager who doesn't know how to do the work, delegating to an employee who does. We wrap the AI in tools: Python, calculators, code execution environments, API calls. The AI generates the instruction, something else does the actual computation, and the AI reports the result. The AI never computes anything itself. And this is where Percepta's work diverges from everything before it. So here's where we are. Transformers are incredible at pattern-based prediction, language, creative writing, summarization, analysis. But they are structurally incapable of exact computation because computation requires deterministic precision and prediction thrives on statistical plausibility. The industry fix is tool calling. Have the AI ask an external program. But Percepta asked, what if the AI didn't need the tool? What if it became the tool itself? That's what we're about to explore, how they actually compiled a program into a neural network's weights, without any training at all. Let me pause and make sure we understand what a transformer actually is, because this is the machine they put the computer inside. A transformer is a specific architecture for neural networks. It was introduced in 2017 by a group at Google in a paper called Attention is All You Need, which is one of those titles that only makes sense after you understand what came before. Before transformers, language models used architectures called recurrent neural networks, RNNs. They processed text one word at a time, left to right, maintaining a running memory of everything they'd seen so far. The problem? If the sentence is long and the most relevant information appeared at the beginning, the model had trouble connecting it to what was happening at the end. It was like trying to remember the first page of a book while reading the last page, but only being able to hold a summary in your head. Transformers solved this with a mechanism called attention. Think of it this way. Imagine you're in a library trying to find information about a specific animal. Instead of reading every book sequentially, you can look at all the catalog cards simultaneously, find the ones most relevant to your question, pull those books, and focus on their contents. Attention works the same way with three components: a query, keys, and values. The query is what you're looking for. Tell me about the subject of this sentence. The keys are like catalog cards. Each position in the text has one. The values are the actual content. What's at each position? The attention mechanism compares the query to every key, finds the ones that match best, and retrieves their values. In practice, this means that when the transformer is trying to figure out what the word "it" refers to in a sentence, it simultaneously compares "it" to every other word in the sentence, finds the best match, usually the most recent relevant noun, and pulls that meaning into its computation. This is powerful. It's why transformers work for language. But here's the critical limitation. To attend to something, the model compares its query to every single key in the input. Every single one. If you have 1,000 tokens, that's 1,000 comparisons. 10,000 tokens, 10,000 comparisons. The work per token grows linearly with the length of the input. In computer science notation, we say it's order of n. And since a transformer processing a sequence needs to do this for every token in the sequence, the total work grows quadratically, order of n squared. That means, if you double the length, you quadruple the work. At the scale of millions of computation steps, this is impossibly slow. Now let me explain why this matters for computation. A transformer generates output one token at a time. Each token requires the attention mechanism to scan through all previous tokens. So if your program execution generates 1,000,000 tokens, The attention mechanism has done a cumulative amount of work that's proportional to 1 million squared, 1 trillion comparisons. You can't run a million-step program with quadratic complexity. It would take millions of years. But there's a way out of this, and it turns on a beautiful mathematical insight. We'll get to it in a moment. First, let's talk about how you normally set a transformer's weights. The answer: you train it. You feed it enormous amounts of data. You measure how wrong its predictions are, and you adjust the weights using gradient descent, a mathematical procedure that tells each weight which direction to move to reduce the error. You do this billions of times, over terabytes of data, on massive clusters of expensive GPUs for weeks. That's how you get ChatGPT. That's how you get Claude. That's how you get every large language model you've ever heard of. The Percepta team did something completely different. Take stock. Transformers have an attention mechanism that compares every query to every key. Order of n per token, order of n squared total. This makes long computations impossibly slow with standard attention. And they're normally trained on massive datasets using gradient descent. Percepta did neither. They used a different attention approach that's order of log n, and they didn't train anything at all. They calculated the weights directly. Which brings us to the breakthrough, the actual compilation pipeline that turns a C program into a neural network. Here's where things get genuinely wild. Most programs, the kind you use every day, are written in languages like C, Python, or JavaScript, and then compiled or interpreted into instructions that a CPU can execute. A C compiler like Clang takes your source code and translates it into machine code, sequences of operations the processor understands. But what is a processor really? At the bottom, it's a collection of logic gates, and gates, Oregon gates, not gates, wired together to perform operations. An adder circuit takes two numbers, adds them bit by bit, carries when necessary, and produces a result. A multiplier chains multiple adders together. A control unit reads instructions and routes data. It's all circuits and signals. WebAssembly is a simplified, portable version of this. It's a stack-based virtual machine with a small set of operations, 35 of them, to be precise. Load a value from memory. Store a value. Add two numbers. Branch to a different instruction. Call a function. Return from a function. Compare values. And a few more. It's simple enough to understand completely and powerful enough to express any program you can write in C. Now here's the Percepta pipeline, step by step. Step 1. You write a program in C. Could be a Fibonacci number calculator. Could be a Sudoku solver. Could be anything that compiles. Step 2. You run it through Clang, the compiler, targeting WebAssembly. Clang produces a sequence of WebAssembly bytecode instructions, those 35 opcodes stacked in order. Step 3. The Percepta compiler takes the WebAssembly bytecode and translates it into the weight matrices of a transformer. Not through training, not through gradient descent on a billion examples, through direct mathematical calculation. Let me repeat that, because it's the most important part of this entire project. They didn't train the transformer. They didn't show it examples and adjust until it got better. They sat down and calculated, analytically, what every single weight needs to be so that when you run the transformer's forward pass, just matrix multiplications and activation functions, it executes the program, step by step, with perfect accuracy. Every number in the weight matrices has a specific purpose. This block of weights implements an addition operation. That block implements a memory read. This one implements a branch. If the comparison says the condition is true, go to instruction 47. If not, go to instruction 53. The transformer doesn't think about what to do. It follows the exact sequence of operations encoded in its weights, like a clockwork mechanism. No guessing, no probability, no temperature settings or sampling. The same input always produces exactly the same output. Every time. It's a computer built out of matrix multiplication. Okay, let's pause and absorb what we just said. The Percepta team took a C program, compiled it to WebAssembly, and then mathematically calculated what the weights of a transformer need to be so that its forward pass executes that WebAssembly program perfectly. No training, no gradient descent, no trial and error. The weights are derived directly from the program's instructions. This is like building a physical circuit, except the circuit is made of numbers in a neural network instead of transistors on silicon. The result is 100% deterministic. The same input always produces the same output. But we still have a problem. Standard attention is too slow for programs that run millions of steps. So how did they solve it? That's the engineering masterpiece. 3 tricks that should make you pause. To run a program, you need memory. You need to store values and look them up. In a normal computer, you have RAM, random access memory. You give it an address. It gives you back the value at that address. Instant. Exact. But a transformer doesn't have RAM. What it has is attention. And attention, as we've discussed, is a fuzzy pattern matching mechanism. It says, this query is probably most similar to that key, probably about 80%. That's great for language, where probable similarity is often what you want. It's terrible for memory, where you need exact address lookup. No, probably. No, 80%. You need exact. Here's what they did, and this is genuinely beautiful. They encoded every memory address as a point on a geometric curve, specifically a parabola. The address 0 becomes the point 0, 0. Address 1 becomes 2, minus 1. Address 2 becomes 4, minus 4. In general, address k maps to the point 2k, negative k squared. All these points lie on a downward opening parabola, a U-shape flipped upside down. Now, when you want to retrieve the value stored at address q, you construct something called a query vector, a direction in this geometric space. And here's the elegant part. The dot product between your query and any stored key produces the expression negative, k minus q squared plus q squared. That expression is uniquely maximized when k equals 0. Always. Every time. It's a mathematical identity. It can't be anything else. So when attention picks the key with the highest score, the strongest match, it will always, without exception, pick the key at address q. Not probably. Always. Let me put that in perspective. They built a perfect key-value lookup system out of a parabola. 2 dimensions. That's all geometry. No fuzzy matching. No approximate retrieval. The math guarantees it. This is like building a filing cabinet out of curved mirrors. The curved shape ensures that any light beam you send in will hit exactly the right drawer, no matter what. So that's trick 1. They found a way to use geometry, a curved line in 2 dimensions, to implement exact memory lookup inside a neural network. The parabola guarantees that a query for address k will always and only match the key at address k, no matter how many other addresses are stored. This replaces fuzzy attention with exact retrieval, which is essential for computation. But there's a second problem. Memory is only half what computers need. They also need logic. Let's talk about the activation function called ReLU. In a neural network, after you multiply inputs by weights and add them up, you pass the result through an activation function. This function introduces nonlinearity. It lets the network do things that simple weighted sums can't. Without activation functions, stacking layers wouldn't give you any more power than a single layer. ReLU is the simplest possible activation function. It takes a number, and if the number is negative, it outputs 0. If the number is positive or 0, it outputs the number unchanged. That's it. X for positive, 0 for negative. Now here's the thing. This simple operation can build any logic gate. Consider the expression ReLU of z plus 1 minus ReLU of z. When z is a whole number, what happens? If z is 0 or positive, both terms are positive, and their difference is exactly 1. If z is -1 or lower, both terms are 0. ReLU kills them both, and the difference is 0. So this expression, ReLU z plus 1 minus ReLU z, produces exactly 1 when z is 0 or positive, and 0 when z is negative. That's a step function, on or off, 1 or 0, true or false. And from a step function, you can build in gates, Oregon gates, not gates, if then else conditionals. You can build any Boolean logic circuit you want. Percepta took this mathematical identity and wired ReLU units together to implement the logic operations that a WebAssembly virtual machine needs. The load instruction becomes, if the condition is true, activate this pathway that retrieves the value. If not, deactivate it. The branch instruction becomes, compare two values, and if the comparison says go left, route the control flow one way. If it says go right, route it the other way. A transformer's feed-forward layer, usually described as a pattern matching device, stops being a pattern matcher. It becomes a CPU. The activation function, which was designed to give neural networks nonlinearity for learning, is repurposed as a digital circuit element. The same ReLU that helps a language model learn grammar is now doing conditional execution. So trick 2. The ReLU activation function, normally the thing that lets a neural network learn complex patterns, becomes a digital logic gate. A mathematical identity turns neural network activations into AND gates, Oregon gates, conditionals. The transformer's internal processing becomes a computer circuit. But we still haven't solved the biggest problem, speed. Here's the biggest engineering challenge. We've established how memory works, parabola trick, and how logic works, ReLU trick. But to run a program for 1,000,000 steps, each step needs to look up the current instruction's key in the KV cache, and standard attention makes every lookup compare the query to every stored key. Order of n per lookup. Millions of lookups times millions of stored keys equals trillions of operations. It would take forever, but Percepta found a way to make this exponentially faster. And it depends on a change to the attention mechanism itself. Standard attention uses a softmax function, which blends every key's score into a weighted average. Think of it as, this key is 30% relevant, that one is 20%, this one is 50%. The output is a mix of all the values, weighted by relevance. But what if you didn't blend? What if you just picked the single most relevant key? This is called hard max attention. The maximum score wins. Everything else gets 0 weight. Hard max attention is more decisive, but it has the same computational problem. To find the maximum, you still need to compare the query to every single key. Order of n, unless you're clever. Here's where it gets gorgeous. In their parabola-based setup, each stored key is a point on a 2D curve. When you send a query, the key with the highest score is always one of the vertices of the convex hull of all the stored keys. What's a convex hull? Imagine you have nails hammered into a board at various positions. Now stretch a rubber band around all the nails and let it snap tight. The shape the rubber band makes, the smallest polygon enclosing all the nails, is the convex hull. The vertices are the subset of nails that actually touch the rubber band. Most nails are inside. Only a few touch the edge. And the beautiful mathematical fact is, for their parabola-based attention, the maximum score, the key that hard max attention would pick, is always at one of those vertices. This means, instead of comparing your query to all n stored keys, you only need to compare it to the vertices of the convex hull. And if you maintain the hull as you add new keys, you can find the right vertex using binary search, order of log n. Let me put numbers on that difference. If your program generates 1,000,000 execution tokens, standard attention, 1 million comparisons per lookup. Across the whole program, 1 trillion total operations. Convex. Hull attention, about 20 comparisons per lookup, because log base 2 of 1 million is roughly 20. Across the whole program, about 20 million total operations. That's a 50,000-fold speed up. Not a margin of error. Not a small improvement. The difference between impossibly slow and 30,000 tokens per second on a CPU. So the pipeline is, as the transformer runs, new keys get added. The convex hull gets updated. Each lookup does a binary search on the hull vertices. The hardmax attention picks the right one, and the whole thing runs at 30,000 tokens per second. Step back and look at the whole picture. 3 tricks, each solving a different piece of the puzzle. Geometry provides exact memory, the parabola trick. ReGLU provides exact logic, the activation as circuit trick. The convex hull makes it all fast enough to actually run, the logarithmic attention trick. Any one of these alone would be a notable theoretical result. Together, they enable a program running inside a neural network for millions of deterministic steps. Let's talk about what they actually ran. They didn't stop with toy programs like addition and Fibonacci numbers. They compiled a real constraint propagation Sudoku solver. The kind that uses backtracking, constraint checking, and systematic elimination. The same algorithm a human uses to solve a Sudoku. Except the human does it with a pencil and the transformer does it through matrix multiplication. Not just any Sudoku. One of the hardest puzzles ever constructed, the Ardo-Incala puzzle. This is a Sudoku so difficult that the person who designed it, a Finnish mathematician called Ardo-Incala, had to invent a new rating system to describe its difficulty. It requires deep chains of logical deduction. You can't solve it with simple observation. The transformer solved it with 100% accuracy. Every candidate elimination. Every logical inference. Every forced move. All through the forward pass of a neural network. The execution trace was roughly 900,000 tokens. Each token a deterministically correct step in the solver's algorithm. Not guessed. Not probably right. Correct. And it did this at approximately 30,000 tokens per second on a regular consumer CPU. No GPUs. No special hardware. Just a C++ program doing matrix multiplication against the analytically computed weight matrices. This is the proof of concept. The Sudoku solver shows that the system handles not just basic arithmetic, but complex constraint satisfaction, backtracking, multi-step logical chains. Real computation. So here's what the Sudoku demo establishes. This isn't a toy. The transformer runs a genuinely complex algorithm, constraint propagation with backtracking, for nearly 1 million steps, with 0 errors, at reasonable speed. Every single step is correct. Every single one. Not close. Correct. The question isn't whether it works. The question is, does it matter? When this came out, the reaction wasn't universally celebratory. 3 major criticisms emerged, and they're worth taking seriously. First, and this is the one you'll see most often, the transformer is roughly 10,000 times slower than running the same program on a real computer. If you want a WebAssembly interpreter that executes a Sudoku solver accurately, you could just use any WebAssembly interpreter on any modern computer. It would run thousands of times faster, use less power, and be thousands of times simpler. Why build a virtual machine out of a neural network when you have, right next to it, a virtual machine made of transistors that already does the job perfectly and much faster? This is a fair question. If the only goal is computation, Perceptive's approach is absurd. Building a neural network computer to run a WebAssembly program is like building a nuclear reactor to power a candle. But the point isn't computational efficiency. And that's what the critics sometimes miss. Second criticism, no training was demonstrated. The weights were calculated analytically, mathematically, by hand. No gradient descent. No learning. The team claims the execution trace is differentiable, meaning you could theoretically compute gradients and train a model to use this architecture. But that claim has not been demonstrated. Without training, this remains an engineering proof of concept, not a new learning paradigm. If you can't train with it, it doesn't change how we build AI. It just means you can encode programs in weights. Interesting, but limited. Third, there's no peer-reviewed academic paper. This research was published on a company blog, with the somewhat smeared aesthetic of marketing pros rather than the careful, detailed methodology and results structure of academic work. There's a GitHub repo, and it's real code, not vaporware. But the absence of peer review means the community can't fully verify the claims. These criticisms are valid, all of them. But there's something both sides of the debate acknowledge. The convex Hull attention trick alone, the order of log n hardmax attention on the 2D parabola embedding, is a genuine theoretical contribution. Even if everything else falls apart, that mathematical result is beautiful, and it could have applications in attention engineering far beyond this project. Let me step back and be fair. The critics have real points. It's slow, it hasn't been trained, and it hasn't been peer-reviewed. But the defenders have a point too. The goal isn't to replace regular computers. The goal is to show that computation can live inside the model. And if the execution trace turns out to be differentiable, that changes the theoretical landscape of what's possible in neural architectures. So let's look past the skepticism and ask the productive question. If, and this is a big if, this approach works end-to-end, what does it enable? Right now, every AI agent architecture works the same way. Claude Code, GPT agents, AutoGen, they all follow the same pattern. The language model generates text. It calls an external tool. The tool runs outside the model, and then the model reads the result back. The tool call is a wall. Nothing computation-specific crosses that wall back into the model's own reasoning. What would change if computation lived inside the model? The execution trace itself becomes part of the token stream. Every intermediate step of the computation, every carry in an addition, every branch decision, every memory access, is a token the model generates. And if the execution is differentiable, gradients can flow through it. This means the model could learn when to compute and when to reason, not as two separate systems, but as two modes of the same architecture. When you need to add two numbers, the model computes. When you need to evaluate whether an argument is sound, the model reasons. Both modes share the same weights, the same architecture, the same context. Think about the implications for coding. If the model can compute internally, it doesn't need to call an external interpreter to check whether code is correct. It can run the code inside itself, see the intermediate states, and reason about those states as part of its own thinking process. Or consider scientific reasoning. A model trying to figure out a physics problem could set up an equation, compute the answer internally with exact arithmetic, and use that answer to reason about the physical situation, all within a single forward pass. No external tools, no context wall. The Percepta team even demonstrated something from compiler theory called the Futamura projection, a concept that says, if you have an interpreter and you feed it a specific program to run, the result is a specialized version of the interpreter that runs that one program faster. They did this with the transformer. They compiled a program directly into the weights, and the resulting model is no longer a general-purpose WebAssembly interpreter. It's a Sudoku solver-shaped transformer, specialized for one specific program. The program text disappears from the input. The computation is baked into the architecture. Partial evaluation. For neural networks, this is the big picture section. If this approach, computation inside the transformer, can be made trainable, it removes the wall between the AI's thinking and the tools it uses. Internal computation becomes part of the model's internal state. Gradients could flow through the computation. The distinction between reasoning and calculating could blur. The Futamura projection, a compiler theory concept, shows that programs can be baked directly into model weights. The potential is that AI could decide when to compute internally versus when to reason probabilistically, all in one architecture. So we started with a paradox. An AI that can write poetry about quantum mechanics and discuss the ethics of artificial consciousness cannot multiply two five-digit numbers without calling an external calculator. A team at Perceptus solved this problem in the most roundabout way imaginable. They compiled a C program directly into a neural network's weights, turning the transformer itself into a computer that solves Sudoku puzzles by running through 1,000,000 exact steps of constraint propagation, all inside a machine designed to predict the next word in a sentence. The irony is part of the beauty. You take the architecture built for statistical pattern matching in human language, and you turn it into a deterministic program executor. You make the poet do arithmetic, not by giving it a calculator, by making the poetry itself the arithmetic. The question isn't whether transformers can be computers. We've seen the proof. The transformer is a computer. It always was. It just wasn't using itself that way. The question is, should they be? Can we train a model that knows when to guess and when to compute? Can computation and reasoning share the same weight space? And if they do, if a single architecture can both think and calculate, what does that make the boundary between intelligence and computation? The team that built a computer inside a transformer might not have finished answering that question, but they've shown us where to look.